So for an overview talk, I thought sort of an interesting approach is I would just give a brief history of NDSolve. So here's an example which would have worked in version, the first version of NDSolve that came out. And that's the solution of the Lorentz equations, which you type it in as a system with initial conditions, and it just works, and you can use parametric plot with it. So that's sort of where we started with NDSolve, and that's still pretty nice to be able to do that, and we've gone a long ways from there. So the brief history of NDSolve starts with Mathematica 2. So in Mathematica 2, NDSolve was introduced, improving the lives of Mathematica users worldwide. That's the way I say it. But I think there are actually three really brilliant things in the very first version of NDSolve that have actually, those are key to its usability and our ability to continue within the same command. I think NDSolve is the sort of the paradigm of a super duper function that has a huge amount of functionality inside of it. And its design is what allows us to just pack functionality in there and keep packing it in and keep packing it in year after year, and still have a very usable command. So a key thing is, like I had those Lorentz equations. Symbolic equations and input. So you just type in a differential equation using d or derivative, x prime, and that's the input. So you don't have to do like you do in MATLAB and write a function for the right-hand side and then do this. I mean, NDSolve automatically does the reduction to first order for a system. It handles resolving initial conditions. So everything symbolic is input, which is just a natural way. Now, if you want to write a function, you can set that up. We've added that as a feature later. You can have vector solutions and stuff. So you have sort of the flexibility of both. But the symbolic interface allows us to do a lot of stuff, including a lot of the differential algebraic equation stuff. I'll be demonstrating a little bit later in this talk. Okay, another thing is interpolating functions for output. So when you look at that Lorentz equation example, the solution came out as something called an interpolating function. We didn't just give a bunch of data points. We didn't throw out data points at you. We gave you an approximate function. And that's what allowed me to do that nice parametric plot, which worked in 3D, which we don't know a priori whether the system's going to be 2D, 3D, or n-dimensional. So that allows a huge amount of users to play with visualizing in many, many different ways. So that was, I think, the second brilliant thing. And then the other thing, which is less obvious in the original design, is they based the algorithms on a method called LSODA, which is the Livermore solver of ordinary differential equations automatic. Basically, that's what it stood for. It was a Fortran package. We adapted from the Fortran, rewrote it in C, and put it in Mathematica. And what that had is that has an automatic selection between BDF methods, backward differentiation formula, which work for stiff problems, and AMS methods, which work for non-stiff problems that are explicit and very fast for simple problems. And sort of having that automatic algorithm selection automatically built in meant that people could just give it their symbolic problem, not have to worry about whether it was a stiff. So they didn't have to decide whether they were going to call ODE 4.5 or ODE 1.2s. They just called NDSolve, and if it could do it, it worked. And it would switch automatically. And we've carried that concept of trying to automatically select algorithms, most appropriate for the problem, out through a lot of the stuff we put in this latest version. So that was version 2, and those three innovations really set us up for being able to do a whole lot. Okay, so in Mathematica 3, we added a few more features. Linear boundary value problems by this obscure Gelfand-Lokodovitsky chasing method, which it took me from reading the paper almost a year and a half to really realize that was just a shooting method specialized for linear problems. But that's how clear the paper was written. But it does solve boundary value problems, and it does reasonably well. And notice again, the boundary values are just given by giving equations for the initial conditions at either end of the problem. Again, a symbolic input. Okay, so here's the other thing was added in version 3 is the ability to solve something like an evolution equation in time. So there's the heat equation. This is a simple model for temperature distribution in the soil. So that was version 3. In version 4, something I realized, and there's all sorts of stuff that was added that I haven't included, so I'm including what I can remember as the highlights. But for version 4, I realized that something was really missing to go to larger scale problems, and that was we needed to be able to store more data points more efficiently with machine numbers. And so that's what really prompted us, and we came up with the idea of the packed arrays, which was introduced in Mathematica 4, which vastly improved our ability to store large arrays. And then in Mathematica 5, NDSolve was completely restructured and modularized interior. Now outside it still looked kind of the same, but there were lots of things added. So we put in lots of new built-in methods. So a general framework for explicit run-and-cut methods, similarly for implicit run-and-cut methods, extrapolation methods, including the A-stable stiffness switching method, and projection methods are some of the highlights there. Also, there's a mechanism that you could actually write your own method and plug it into NDSolve. And some people actually developing methods were using that at various points. We added the capability of handling differential algebraic equations handled by the IDA solver, which is also another solver from Livermore, though Livermore has now advanced to actually writing things in C, so it was much easier to adapt. Solution for array value dependent variables, so you could give an initial condition as an array or a vector, and it could just solve with that. And also much better handling for the 1 plus n dimensional evolution equations like the heat equation, but in multiple space dimensions. So the code was reworked to take advantage of the speed of packed arrays. And new thing coming in sort of right around version 5 was sparse arrays. So we actually improved to using sparse Jacobian computations for doing PDEs and actually any NDSolve computations and pseudospectral methods for PDEs. There's also a bunch of NDSolve context functions, which many of you have never used, but they sort of control the whole thing under the hood, so to speak. And those are useful for some of the things we're introducing now. There's an NDSolve process equations, an NDSolve iterate, which actually does the time integration, reinitialize, and online advanced documentation that it goes into all the gory details of how the methods work, lots of examples. It's actually, I think, still a really useful reference for NDSolve and differential equations in general. So one example that we can now do was this tsunami example, and so we set up the shallow water equations like this. So this is the height of a wave as a function of longitude, latitude, and time. And so we're basically, it's a shallow water approximation. I set up a couple of seamounts as an example. We can solve this equation in 32 seconds. And actually what takes the most time in this is to set up this animation. So NDSolve solves it much faster than this animation sets up. But we have this nice animation. We start with sort of a wave, and it propagates over various seamounts, and you see how the tsunami. So it's a very simple tsunami thing, but being able to type it in just a few lines like that is pretty good for a prototype model. So that's what we're able to solve much bigger problems with the improvements we made in version 5. Okay, in Mathematica 6, we added a shooting method for nonlinear boundary value problems. We added dense output, or continuous output is what some people call it, which is accessed by using interpolation order all, so that gives you very smooth solutions. We added an event locator method that allows you to set up events, and we're taking that to the next step in version 9. I'll be showing you this soon. And we added stabilized Runge-Kutta methods, and those have been improved now to ROC methods. In version 7, we added delayed differential equations, or DDEs, and improved step and stiffness control. In Mathematica 8, we continue to improve NDSolve, but probably the biggest thing that affected NDSolve was I put a lot of work into the Mathematica compiler. And so the Mathematica compiler was improved to the point where we could compile the equations given to NDSolve much better, much more efficiently, so it actually just runs faster under the hood. And so finally we come to version 9. So one is NDSolve has been sitting all by itself for all these years. Now it has brothers and sisters. So it has a bunch of new commands called NDSolve value, parametric NDSolve, and parametric NDSolve value. Probably the important ones of these are parametric NDSolve value, and I'll use a couple examples with NDSolve value. They're just sort of shorthand things, but parametric NDSolve value is a real advance. The method option has been changed a little bit. You can still use the method option just as you have before to specify a time integration method, which is how it was typically used. But we decided there were so many stages and processes of solution that NDSolve goes through, we had to differentiate those because some of those were orthogonal to each other and it was getting confused which method went where. So we separated those into 6 separate stages, and for some cases even more, that goes on. So there's a time integration. So you can give method goes to, then time integration goes to whatever method you want to say, like explicit Runge-Kutta would be a time integration method. And I'll give some examples of these. Boundary value problems would say, what method do you want to use for boundary value problems? How do you want to adjust that? Discontinuity processing, this is a new version 9 feature. We do some automatic discontinuity processing. I'll show an example of that. Equation simplification. We used to have this solve delayed option, which is a little bit confusing as to what it actually meant. So now we say, how do you want to simplify the equations? Do you want to solve them for the right-hand side? Do you want to write them sort of as a mass matrix form of DAE? Or do you want to just get a residual and solve as a DAE? So that you can specify what to do there. Index reduction. So we now have index reduction for differential algebraic equations. You can specify how to do that. We have special code for initializing DAEs, which actually is sometimes the hardest part of solving a differential algebraic equation system is the initialization itself. And finally, something for PDE discretization. So another new thing is a new command. This goes inside the equations for NDSolve. It's called winEvent, and it specifies when something happens, take some action. And I'll show an example of how that's used. Another option, discrete variables. So you can specify some variables to be continuous variables that have derivatives, and others that are discrete that only change at certain times. Basically, they only change within winEvent occasions. Automatic discontinuity handling. Parametric solutions. That's going to be the parametric NDSolve. And finally, this is the final feature I'm going to talk about, is enhancements for DAEs. These are enhancements for differential algebraic equations, sophisticated initialization. Okay, so let's go to some of the new events. I mean, one is this ability to solve so-called hybrid systems. And hybrid systems is kind of a buzzword to describe a dynamical system that has both discrete and continuous behavior. And here's I think a fun example. Is suppose you set up a block on a moving conveyor belt, or you turn your belt sander upside down and put a block on it, turn it on with a spring attached, okay? And what's going to happen is the conveyor belt's going to tend to move this out, and then eventually the spring force is going to overcome and it's going to snap back, okay? Now we're going to assume that there's sort of we're going to set up a friction model. So let's assume we have a linear spring. Okay, and we're going to use a so-called Strybeck friction model, which looks like this. And I'm not going to explain it. I'll just show you the graph for this. So basically, when the block is stopped, it has very large, essentially static friction. But as soon as it starts to move, that friction goes down. So there's sort of a discontinuity point here and here. So basically, once the friction gets large enough for the block to go through zero velocity, it essentially stops, it sticks, and then once the force gets large enough to overcome these, then it starts to slide again, and it starts to, it gets into this region quite quickly and moves. So it's sort of it's a smoothing of the Coulomb type friction model with a static friction. It's thought to be a slightly more accurate model. That sort of tries to mimic some of the molecular level stuff, but who knows if it really does it or not. So here's what the differential equation is. So I have two forces here. I have a differential equation is F equals ma. Here's the acceleration. So if I'm setting up now a discrete variable, which I'm going to call s. Okay, if it's sticking, then s is 0 or 1. Okay, and if s is 0, then the force is just going to be the velocity of the rate of change, the acceleration is going to be the velocity of the rate of change of the belt. And I'm going to make the belt go to constant speed, so that actually is going to be 0. So VB is the velocity of the belt. For the example of this demo, I'll make it 0. Okay, so here's the force of the spring, Fs. Okay, so that's the case where it's S is 0, it's sticking, it's just going to have that force. But if it's actually moving, it's going to have the force of the spring minus the force of the friction is going to oppose the force of the spring, and minus the movement of the belt, which tends to make this thing move along. Okay, and that's it. So I give it an initial condition, and that's going the force of the friction is going to depend on S of t, because if S is so let me enter that. And then, so the one other thing I need is I need a transition from sticking to friction. So I'm going to set up actually 3 events. Okay, when the speed of the block equals the speed of the belt, that means it's moving exactly with the belt, and that's the static friction situation. So I set S to 0. So I have S is 0 when it's static, essentially the static friction. Otherwise, when the force of the spring gets large enough or small enough, I set S to either 1 or minus 1, depending on, and that takes care of the sign of the friction in there. I mean, I could do it with a single value, but it's easier to do it with the 3 values there. Then I know which side I'm on. The integrand event goes to true. Tell it to use a very robust method for finding the event so it doesn't miss the events. So now I set some parameters. I set the equation to solve. Okay, it solves it, and here's the plot of the solution. Now, what does that actually look like? It's kind of hard to visualize that. But basically here, it's static, moving along with the belt, then it slips. Static, slips. And I'll just show you a quick animation that shows that. And it moves along the belt, and then suddenly it moves back. And that's the classic stick-slip situation. Okay, so let's go to the automatic discontinuity handling. So something that NDSolve is able to do now is this equation. Okay, so let's do this. Okay, so here I've set up a little oscillator, x prime equals, but it's got an if in it. So if the velocity is greater than 1, then the acceleration is minus 1. It's a little bit artificial. Otherwise, it's minus x. So it's just like a harmonic oscillator, but if the velocity ever gets to be greater than 1, the acceleration is minus 1. Okay? And here's what happens. So it's just like an oscillator, which is growing. It's actually, I put in a negative damping, so it actually grows. And then it grows, but it grows until the velocity gets bigger than 1, and then poof, gets flattened off. And in these cases, this is something called, and then it goes like this forever. This is called sliding mode here. It gets into a situation of sliding mode, and I'll show you why it's called sliding mode by showing you the phase plane. Okay, so this is the same situation. Okay, here's the vector plot. Okay, so we start with the thing here. It grows outward. Notice how the vector field is pointing towards this line from both directions. So basically, the trajectory gets sandwiched along that line because the vector field's pointing in both ways. And that's when it gets into what's called sliding mode. And you can't, you're not able to, if you don't take into account of that continuation, the ODE solvers will just sort of chatter and not really get a decent solution at all. So you have to account for it somehow. And then as soon as this starts to point down a little bit, it escapes sliding mode, it comes around. So this actual outer orbit is arbitrarily stable. It eventually gets there in finite time, and it stays on that orbit forever. So the sliding mode is actually sort of a super stable situation. And that's just handled automatically by Mathematica handling the if and setting up events to handle that situation automatically. So let's look at Parametric NDSolve, and this is one of the new commands. Okay, so Parametric NDSolve value. The value after the NDSolve means instead of returning rules, what it does is it just returns the value for as if the rules were replaced for the third argument. So this returns the value of x given this. So this is all the same as NDSolve, except we've added one extra argument here at the end. And those are what things are expected to be considered as parameters. So here A and B are considered to be parameters. One is part of the equation, and one is the initial condition. And what it does is it returns, instead of an interpolating function, it returns a parametric function. And then if I give the parameter values to the parametric function, it computes and it returns an interpolating function approximation for x. Okay, now that could be, say, x of 10, in which case it would just return the number for x of 10. Okay, so that's how, so there's an extra layer of function here. Let's actually plot some values. So here I've done several values of the function for this, 2 plus or minus epsilon, just small changes around a value. And so notice what I'm giving is I'm giving p values of the parameters. That's going to give an interpolating function. Then I do it of t. That's the function I'm plotting with respect to t. Okay, now something this allows you to do, and here's another plot. It allows you to do the following. I'll just show this one. Notice that I'm using the derivative of p fun with respect to a. So I can get the derivative of the solution with respect to the parameter, which is often called a sensitivity solution. So actually what we've done by packaging this to this parametric function is we've made sensitivity solutions available to you just by the simple act of taking the derivative. That's all you have to do to get sensitivity, which I think is pretty neat. And so this actually shows the sensitivity with respect to the parameter a of this central solution, with some scaling. Something this allows you to do really quickly by having the sensitivity. So suppose I set up a slightly artificial example where I set up some data, which is a perturbed value of a solution of a differential equation. And suppose I want, this is the same equation, and suppose I want to find out, well, what parameter values would have led to this data if I'm modeling this differential equation. Well, I can actually just put this parametric function of AB into find fit. Okay, I've got the data. I can give starting values for the parameter. It gives a message in this case that has to do with the randomness. Sometimes it does, sometimes it doesn't. And you see it finds a pretty good fit. And because it has the sensitivity of the derivatives, it's able to use that fit very efficiently. So fitting to differential equations. And finally, the last example I'll show is differential algebraic equations. Okay, and here's an example of an equation for a double pendulum. So if I enter this equation, it's fairly complicated. It's 2 equations. It's basically that situation set up, but just set up as a constrained system. So we're not thinking about converting to angles and theta. We're just talking about x1 and y1 is this position, and x2 and y2 is that position, and the constraints are only the length. And lambdas are basically introduced as Lagrange multipliers, but those are essentially the tension on the strings or the sticks holding the things. So if we try and solve this without index reduction, NDSolve gives a message that says it failed. So the DA solver, it actually found initial conditions, which is pretty impressive for this system, given the stuff I started with. But it says the solver is intended for index 1, and we do a structural analysis. The index is actually 3. That's the structural analysis indicates that, and that actually is indeed the index of that system. So it's an index 3 system. So to actually solve it with the methods we have available, you need to do some kind of index reduction. So I can say, okay, let's solve this. I'm going to use index reduction using the Panelides method. And I want to handle the constraints that are left over from index reduction using the projection method. And these messages will probably hopefully clean up. Those come out of the projection method. They're completely unimportant. At this point, I get a solution. And then to show you what that looks like, I have a fun little animation. It takes a little while to set up the animation. But so the thing is, by reducing the index, we're actually able to get an effective solution of that equation. And there are higher index solvers, they do exist, but higher index problems just are much harder to work with. So here's my simulation of the double pendulum, and I started from a rest position, and I think that's pretty fun to be able to just basically type the equations in a completely straightforward way and just have it work. And it actually took longer to generate the animation than it did to solve the equation by quite a bit.